Right, I'm going over an Edexcel paper. It's Combined Science Physics, paper 1 from 2022, foundation tier. You get 1 hour and 10 minutes and it's worth 60 marks. Question 1, Part A. Figure 1 shows how the visible spectrum of white light is shown on a screen. Which of these is the best piece of equipment to produce the white light? That'll be a ray box. Part 2. Which colour is seen between yellow and blue in the spectrum on the screen? Richard of York gave battle in vain. Red, orange, yellow, green, blue, indigo and violet. So what is between yellow and blue? Yellow and blue. It's green. Part B. Figure 2 shows the main parts of the electromagnetic spectrum. Complete the following sentences using information from Figure 2. Each part of the electromagnetic spectrum may be used once, more than once, or not at all. Part 1. The part of the electromagnetic spectrum used to detect broken bones is X-rays. Part 2. The part of the electromagnetic spectrum used in thermal imaging is infrared. Part 3. The part of the electromagnetic spectrum that is used to cook food and has a shorter wavelength than microwaves. That's infrared as well. Because radio over here is all long and then the wavelength gets shorter and shorter and shorter as you come over to there. Part 4. The part of the electromagnetic spectrum that is used to sterilise medical equipment and has a shorter wavelength than X-rays. Well, there's only one and that must be gamma. Gamma's got loads and loads of energy. It sterilises things because it kills bacteria because of how much energy it's got. Question 2. This question is about waves. Part A. Figure 3 is a diagram of a water wave in a ripple tank. Part 1. State the number of crests of the wave between P and Q. So there's P, there's Q. These are the crests of the water waves, the lines. So you've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Part 2. The distance between P and Q is 42 centimetres. Calculate the wavelength of the water wave in figure 3. So you've got 42 centimetres of distance and that's going to be 12 waves. So 42 divided by 12, that means that each wave was 3.5 centimetres. And remember, the wavelength is just the length of one wave. Part 3. Describe how a student could determine the wave speed of the water wave in figure 3. Right, there's a couple of ways you can do it. You could wait for one of the waves to pass P and then start your stopwatch and then stop the stopwatch once it reached Q. And I get the speed, just do distance divided by time. And we know the distance was 42 centimetres. The other way to do it is to see how many waves go past P in 10 seconds and then do the number of waves divided by 10 seconds to get how many waves there are in 1 second. In other words, get the frequency of the waves. And we know what the wavelength is. It was 3.5. So then you can just do wave velocity equals frequency times by wavelength. So let's write that down. Time a wave moving from P to Q and then speed equals distance over time, or count the number of waves passing P in 10 seconds. Work out the frequency of the wave by doing the number of waves per second. Then do velocity equals frequency times by wavelength. So it's probably easier for 3 marks just seeing this. Part B1. Which row of the table is correct for sound waves? So sound waves are longitudinal, so it's either that or that. Can sound waves transfer energy? All waves transfer energy, so the answer is yes. So the answer is A. Part 2. A sound wave has a frequency of 440 Hz, so that's F, and a wavelength of 0.75 meters, that's lambda, the wavelength. Calculate the wave speed of a sound wave. So that's V is our target, question mark. So the wave velocity equals frequency times by wavelength. Let's put the numbers in. So that's 440 Hertz times by 0.75 meters. And that comes out as exactly 330. And that'll be meters per second. Question 3, Part A. Figure 4 shows a truck lifting a box. The box has a mass of 57 kilograms, so that's M. The truck lifts the box to a vertical height of 2.1 meters, that's H. The gravitational field strength G is 10 newtons per kilogram. It always is on Earth. Calculate the change in gravitational potential energy of the box, that's GPE. Use the equation. So we just need to pop the numbers in. Mass times by gravity times by change in height. So that's 57 kilograms times by 10 newtons per kilogram times by 2.1 meters, and that comes out as 1197, and that'll be joules because it's energy. All energy is measured in joules. Part B. A cyclist of mass 70 kilograms, so that's the mass M, travels at a constant velocity of 8 meters a second, so that's V. Calculate the kinetic energy of the cyclist. So kinetic energy is our target, and we need to know that kinetic energy equals a half times by the mass times by the velocity squared. Let's put the numbers in. So that's a half times by 70 kilograms times by 8 squared, and remember to do the 8 squared first, and that comes out as 2,240. Once again, that'll be joules. And remember to type a half into your calculator as 0.5. Part C. Figure 5 shows a trolley at the top of a slope. A student gently pushes the trolley until it just starts to roll down the slope. The student measures the time it takes for the trolley to roll down the slope. The student repeats this for different values of the angle alpha. Figure 6 is a graph of the student's results. Part 1. Use the graph in figure 6 to find the time the trolley takes to roll down the ramp when the angle alpha is 45 degrees. So there's your angle. That's 40 and that's 50. Then 45 is right in the middle. And that comes out as, if that's 0.5 and that's 0.6, then that'll be 0.54. And that was the time, which is what they've asked. Part 2. Use the graph in figure 6 to estimate the time the trolley takes to roll down the ramp when the angle is 80 degrees. Right, we're going to have to continue the graph. So it's coming down like that, it's starting to curve, and it's going to come over there like that. So from 80, if we do the dots up to 80 again, the examiners love that. And you're looking at about 0.44. They'll always accept a range though, so anywhere between sort of 0.42 up to about 0.48. Part 3. The student had a choice of how to measure the time the trolley takes to roll down the ramp. 1. Use a handheld stopwatch. 2. Use light gates at the top and bottom of the slope. The student chose to use the light gates. Explain why this was the correct choice. You should refer to the data on the time axis of figure 6 in your answer. Right, well, if you're going to use a handheld stopwatch, that is human reactions, which are about 0.25 seconds, about a quarter of a second. Now, what is the time we are trying to measure? The time we're trying to measure is between anything from 0.4 up to 1.1. Now, that time is too fast for humans to measure. Our reactions are just not fast enough. Human reaction time is about 0.25 seconds. Which is about the same time that the student is trying to measure. Our reactions are not fast enough. That's why he made the right choice to get the computer to do it using light gates. Question 4, Part A. Figure 7 shows a safety sign on the door of a laboratory where radioactive materials are used. Part 1. State one way that radioactivity can be dangerous to humans. Right, they damage cells, cause cancer. That's the easiest way of getting a mark. I usually say both of those things just in case it's worth 2 marks next time. Other things you could say is radiation sickness or radiation poisoning, mutation of DNA, burn your skin. Part 2. State one piece of equipment that can be used to measure radioactivity. Right, that's a Geiger-Muller tube or counter. Or you could just say a GM tube, because it's easier to remember. You can use photographic film. Turns from clear to dark. Or you could use a dosimeter badge, which has basically got the photographic film inside of it. Part 3. Alpha radiation and ultraviolet radiation are ionising radiations. Give 2 other ionising radiations. Well, you can have alpha, beta and gamma, but they've already said alpha. So we could have beta positive, or you can have beta negative. So this is what we call a positron. This one is just normal beta radiation. You can have gamma radiation, or you could have X-rays. Part B. Sulfur 35 is a radioactive isotope of sulfur. Figure 8 represents a nucleus of sulfur 35. Draw one line from each type of particle to the number of that type of particle in a nucleus of sulfur 35. So the type of particle, a proton, how many particles has it got? Right, well that's the proton number on the bottom, otherwise known as the atomic number. So that's 16. Right, the number of neutrons. Well, this number here is the number of neutrons added to the number of protons. So if we do 35 take away 16, that'll tell us there are 19 neutrons. That's neutrons plus protons. Take away the number of protons, that'll leave the number of neutrons. And it's what you call the mass number, or the nucleon number. Now, the nucleon just means anything that's in the nucleus, which of course is the neutrons and protons. Oh, and that's what it's asking for next, nucleon number. So that's just 35, which was the top number. Question C. A sample of a radioactive isotope has a mass of 520 grams. The half-life of the radioactive isotope is 18 days. So remember, the half-life is just how long it takes to half. Calculate the mass of the original radioactive isotope remaining after 18 days. Right, well, it's just going to half once. So you're starting with 520 grams. 18 days later, it'll half. So that'll just be 260 grams. Part 2. Calculate the mass of the original radioactive isotope remaining after 54 days. So 520 grams at first. 18 days later, it's going to half down to 260 grams. Another 18 days, so that's 36 days in total. It's going to half again, so that's 130 grams. And then we still haven't reached the 54 days, so another 18 days, so that's the 54 days in total now. It's going to half again, so that'll be 65 grams. And that's exactly how I would set it out. And if they do ask, how many half-lives was that? It was 1, 2, 3 half-lives. So if you did 54 days divided by 18 days, which was the half-life, that tells you that there was 3 half-lives. Question 5, Part A. Which statement describes conservation of energy in a closed system? So closed system means that nothing can get in or out. When there are energy transfers, the total energy reduces. No, nothing can get in or out. When there are energy transfers, the total energy does not change. Yep, that could be it. When there are no energy transfers, the total energy reduces. Nope. When there are no energy transfers, the total energy increases. No. So the answer was definitely B. Part B. The student uses the apparatus in figure 9 to find out which of two materials, sand or sawdust, is the better insulator. The student also has a kettle to boil water, a thermometer and a stop clock. Draw a label diagram to show how the student should set up the equipment to investigate which material is the better insulator. Now, this caught a number of students out a few years ago, so this is how you set it up. So make sure you label the diagram, like I have. I think what caught people out is they didn't realise that you had to use the kit twice and set the whole thing up over here, perhaps, but next time with the sawdust. Now you'd only have to draw it once. You wouldn't have to draw this one as well. I'm just drawing it twice so you know first time put the sand in as your insulation and do all your measurements, and then the second time put the sawdust in as your insulation and see which one was better. Time it. See which one keeps it hottest for longest. Part 2. Give 3 factors that the student must control in this investigation. Right, how are you going to keep it a fair test? You'd better make sure that you use the same amount of water. You'd better make sure that you use the same amount of insulation or mass. And you'd better have the same temperature. Also the same starting temperature. And you could say leave them for the same amount of time. Leave to cool for the same amount of time. Same amount of water. Same amount or mass of insulation. Same starting temperature of hot water. Or leave to cool for the same amount of time. Question C. Expanded polystyrene used to insulate buildings has different densities. Figure 10 shows how the thermal conductivity of expanded polystyrene changes with the density of expanded polystyrene. Using the graph in figure 10, describe how the thermal conductivity of expanded polystyrene changes with the density of expanded polystyrene. Right, so that's low density and this is high density. So as the density increases, the conductivity decreases. And whenever it's not a straight line, so whenever it's a curve, doesn't matter which way it curves, you see it's non-linear. If it was a straight line, you'd say linear. Part D. Figure 11 is an energy diagram for an electric kettle used to heat water. So this is the energy supplied to the kettle in 1 second. That's the energy lost to the surroundings in 1 second. Mind, that's a bit cheeky. Normally they have the useful energy up here, so be careful. Energy used to heat the water in 1 second. So this is the useful energy in this particular case. Part 1. Calculate the amount of energy lost to the surroundings in 1 second. So they're just saying in 1 second, 1 second, 1 second. Don't let that put you off. Right, what goes in must come out. We've put 3,000 joules in. We've only got 2,400 joules that's came out. So the energy that must have been lost is the difference. So 3,000 take away 2,400, so that's 600 joules has been lost in 1 second. Part 2. Calculate the efficiency of the kettle. Use the equation. Efficiency equals useful energy transferred by the kettle in 1 second. So that was 2,400 joules divided by the total energy supplied to the kettle in 1 second. So the total energy supplied was 3,000 joules. And that comes out as 0.8. And if we multiply that by 100%, that would equal 80%. Might have been better just to leave it as 0.8 since they didn't ask for it as a percentage. Question 6. Part A. Figure 12 is a speed limit sign from a European motorway. The speeds shown are in kilometres per hour. Part 1. The sign tells drivers to drive at a slower speed in wet weather. Explain why it's safer for drivers to drive at a slower speed in wet weather. But when it's wet, there's less friction between the tyres and the road. And that will mean there's an increased stopping distance. You might end up crashing into someone because you can't stop quick enough. Another way of saying it, slower speed means a shorter stopping distance. And if you're going slower, means that you'll probably not skid or slide or lose control or crash. So you decide which of those responses you prefer. Part 2. Show that a speed of 31 metres per second is less than a speed of 130 kilometres an hour. Right, so there's a couple of ways of doing this. We can either convert 31 metres per second into kilometres per hour and see how that turns out. So divide that by 1,000. So that's 0.031. And that'll be kilometres per second. But we need to see how many kilometres it is per hour. So I'll need to multiply it by 60 because there's 60 seconds in a minute. And then we'll need to multiply it by 60 again because there's 60 minutes in an hour. And that'll equal 111.6 kilometres per hour. And that's proved that it's less than 130 kilometres an hour. The other way to do it is to convert kilometres an hour into metres a second. So that one was converting metres per second into kilometres per hour. Right, so 130 kilometres per hour. If we multiply that by 1,000, that'll tell us how many metres per hour. So that's 130,000 metres per hour. And we want metres per second. So if we then divide that number by 60, because there's 60 seconds in a minute, and then also divide it by 60 again, because there's 60 minutes in the hour, just like before, and that'll come out as 36.11 metres per second. So once again we've shown that 31 metres per second is less than 130 kilometres an hour, because 130 kilometres an hour is 36.11 metres a second, which is more than 31. So again, you decide which way you find it easiest. Part 3. The driver's reaction time is the time between the driver seeing an emergency and starting to brake. So that's what we say between seeing a stimulus and then starting to brake. That would be your response. And between there and there is the reaction time. The car is travelling at a speed of 31 metres per second, so that is our speed. The car travels 46 metres, so that's our distance. Between the driver seeing an emergency and starting to brake, calculate the driver's reaction time, so that's our target. Give your answer to two significant figures. Right, well, speed equals distance divided by time, and we need time. So we'd better shove it into a magic triangle. So distance is on the top shelf here. So it goes on the top shelf here. And then I've got two spaces and two things. So just shove those things in those spaces. Cover up what you're looking for. We're looking for t. And we are left with distance divided by speed. So time equals distance divided by speed. Put the numbers in. The distance was 46 metres. The speed was 31 metres per second. And that comes out as 1.4838 seconds. Now they want it to two significant figures. So the first significant figure is any number that is not a zero. So this first number is not a zero. So that's your first significant figure. And then that's your second significant figure. And of course, look at the third one. And in this case, it's going to round the 4 up to a 5. So your answer is 1.5. And finally, question B, our 6 marker. The last question. Figure 13 is a velocity time graph for a toy car on a straight track for 7 seconds. Using information from the graph, describe when and how the velocity and the acceleration of the toy train change at different times during the 7 seconds shown on the graph. Right, so we need to talk about the velocity. Well, first things first, if it's talking about the acceleration, let's write down that we know that the gradient of the graph, so how steep the graph is, that tells us acceleration. And we also need to talk about the velocity. Right, so at a time of 0, the velocity equals 0. Right, the velocity increases for the first 2 seconds. So it accelerates for 2 seconds. Then the velocity reaches its maximum between 2 seconds and 4.6 seconds. And it is a steady velocity. So that is between the time of 2 seconds to 4.6 seconds. Right, then the velocity decreases quickly for 0.4 seconds. So the velocity decelerates quickly for 0.4 seconds, and that was from 4.6 seconds up to 5 seconds. They've asked us to say what was happening at the different times. And finally, it decelerates again, but more slowly, between 5 to 6 seconds. So the velocity decelerates more slowly for 1 second, between 5 and 6 seconds. And they want to know for the full 7 seconds, so let's not forget this last little bit. Once again, the velocity has gone back down to 0. So the velocity is 0 for 1 second from 6 to 7 seconds. And we should get 1, 2, 3, 4, 5, 6, 7. We've easily got our 6 marks there. So that's how to answer that paper. Hopefully you've learned more about physics by going through the paper. Good luck with any exams you're sitting, especially if it's for your GCSEs this year. Work hard, be nice, and I'll see you in the next video. Want to see more videos like this? Subscribe to my channel, GCSE Physics Explained.